Hey, well, welcome. Welcome to the last class. You made it this far, so that's a good thing. Um, Let me see. We're going to talk about handouts 19 and 20 today. And 20 is just some notes, but I just wanted to put that on a piece of paper so you had it. It seems less random that way. Let me let somebody in. Okay. So I've uploaded the problem set, and also in there you have office hours. And so I added some extra things to that, like there's two problems where you have to do some research. One is you'll have to read an article about the priority dispute, which I'll just talk about briefly and comment upon that. So, write a reaction to that similar to what you did with Archimedes. And the second is that I'm asking you to, I was going to give you some follow-up to Archimedes, and so what it ended up being was you either have to look up something about pi and and talk about what he did to approximate pi. You can make a catalog of the contents of his contents from the palimpsest and write like a sort of like a catalog. You'd write a paragraph or two about what's in each one, or you can come up with something on your own based on your reactions or my comments to your reactions that I return to you. So that has a little bit less form to it. And then the rest of them are standard questions from stuff that we haven't had the problem set on. So hopefully that's pretty clear. I would not wait to the last minute because you have to read something, and I think when you read something and write about it, the more you think about it, the better. And so one thing I like to do is read it, put it down for a while, and then come back to it like a day or two later, and then I find out that a lot has gone on that I'm not aware of, and thinking about it, and then I read it again, and it makes a lot more sense. So anyway, and the article is longer than it looks because it's a book review, and the thing that I'm most interested in is their discussion of the priority dispute, not so much a review of the book, even though there's some useful information in there. Okay, and so evaluations, I hope you've had a chance to do them. If we may end early today, it's my hope, and then you would have some time there, and it's available till 7 o'clock tonight. So, and again, I've mentioned before why I find those helpful and why, how Drake uses those. Okay. So today what I wanted to do, actually, let me pause for a second. Are there any questions about any of that stuff? Okay. 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 I wanted to just show you a little bit from Leibniz, just a little bit about like what does math look like, and you'll see why I'm doing that. And I'll share the screen to do that. I'm going to talk briefly about, what Newton and Leibniz did, to kind of compare, contrast, just very briefly. I'm going to talk very briefly about the priority dispute between them, because you're going to find out more about that. And then I want to focus in on one aspect of what Newton did with calculus, just to try to give you a flavor of how he thought about things. I think it's a really good idea. I mean, this is relatively simple. It ties into stuff that you've done before in calculus. And so I think it just is a good way to sort of give it insight into how he viewed things. And whenever I look at Newton and Leibniz, I would say I should do a whole course on them, because there's just the whole idea of how calculus came about and what their thoughts were, I think are really, I find it really interesting. And the 2 classes I spend on it barely do any, it just scratch the surface. So, okay, so I'm gonna, and I'm recording this too. I think I remembered to do it. Just want to double check. Yep. So I'm gonna share the screen, and I'll go to the class site, and I just want to make sure that when I navigate it, let me get to the web page I want to get to first. That way, I know sometimes it doesn't follow. So just give me a second. And where I'm going to is the readings and the folder on Leibniz. And there's a you'll see it in a second. Okay, so are you seeing it says Newton Leibniz priority battle at the very top? It says Newton. Okay, so what I did is this is a link to some of his works. I mean, these people wrote a lot, and often it's in letters and things that were a lot of information then was was communicated by letters among mathematicians. So it was a way of publishing. You know, they didn't have the journal structure and the sort of the university structure that we do, even though there were universities, of course, to disseminate information. So there was a lot of private correspondence. And anyway, so that it includes that and some other things. And I'm going to go here, and I want to go to page 49, which I think here, because of the pagination, is going to be 55, but it's actually page 49. There it is. And there you see what he calls the arithmetic triangle. And then you go below it and you see a version of the thing that I gave. I mean, here you go up slants to make summations, and the one that I gave, you go up and down columns. So so this is how he presented it, and he's writing in the third person for some strange reason. I don't understand why, but he's doing it that way. So when he talks about his friend, he's really, or when he talks about Leibniz, he's talking about himself. And so if you look down here, you see he starts summing things, and when he sums up the harmonic series, which we know diverges, he writes it as 1 over 0 for infinity. And then he does some of the things that we were, you know, this column is the not this column, but it's what we ended with, where he multiplies this column by two. So, and I'm just pointing this out just so you can see it. And here he starts to formalize it and starts to make equations for the series. And so he's already formalizing it. And if you read through this, you see that he starts to apply some of the things that he's learning from the triangle into his development of the calculus. We don't have time for that, but I wanted to look on page 55, and I'll blow it up a little bit. And look at the fourth line, and what do you see there? So right here. Does that remind you of anything? Here, let me annotate. You're not seeing what I'm doing. Sorry about that. Hopefully you can see that, and does that remind you of anything? And think of U and V.
Kind of like an integration by parts type thing?
Exactly. If you move, let's see, if we move this over here, then we have integration by parts. And there's a couple of reasons I'm showing you this. Because this is his writing, so you can see it looks pretty familiar. And it's notation that he created that we still use. Actually, I had it backwards, but that's all right. No, I think that's right. Anyway, it doesn't matter. So, and if we had done this face to face, when there's, you know, things go a little bit more efficiently, I would have shown you how he figured this out, and then you can use this, as I believe he did, to find out all the integrals. You know, like you can use the integral of x to find the integral of x squared, use the integral of x squared to find the integral of x cubed. And I didn't ask that. It's on the handout, but we just didn't have time to get into it. So anyway, I just wanted to give you a little bit of a very, very brief flavor of what it looked like and what he did. And you see that it doesn't look unfamiliar. I mean, it's his notation that, you know, that we use in so many different things. And he was very interested in the notation and rules for looking at the notation. So just keep that in mind. So I just wanted to show you that briefly. So kind of is to tie up a loose end, and then to show you the context, or a little bit about the context of where that triangle came from. Okay, and this is translated. He was German. I believe he wrote. I think this was originally written in Latin, and then it's, you know, obviously it's been translated. Okay, so any comments or questions about that? Just wanted to give you a brief flavor of what that looked like. Okay. So what I wanted to talk about next is I'm going to go to the handouts. And so just go to the 20th handout, and it's just some bullet points that I just wanted to sort of give you a sense. Sorry. Sorry, I'm not sharing the screen, so it's okay. So you have that to look at, so I'm not going to share. but I just wanted to sort of give you a little flavor of, I'm doing sort of episodes from each of their mathematics, but just to give you a little sense, a better sense of the bigger picture. And so the first thing I'm talking about is that people were finding areas and volumes, and people were finding tangents and subtangents and things like that. You saw that example with Fermat, and it was it was doable, but it was convoluted, I would say at best. And so what they did is that they realized that the same general principles were involved in both the problem of tangents and finding areas. And so if we looked at finding areas, you would see they're very similar if you did this before you learned integration, where you had to find the area under a curve by hand. They were those kinds of problems, but even more convoluted and less straightforward. But people knew how to do both of those things, and for all throughout the 16th century. So finding an area, finding a tangent, there were lots of methods for each, but they were not related. And so what one of the things that they did, that both Newton and Leibniz did, that was genius, was to connect those two and to realize they were inverse problems. And so if you look at the fundamental theorem of calculus in a book, it's maybe not the most important thing that you do, or it's not the thing you use the most in calculus. It may or may not be. But the reason that it's so fundamental is it's sort of paying homage to that understanding that those two processes are inverses, and there's no reason by intuition why they should be, or at least not easy intuition. Like if you just look at the problems, you're not going to say, oh, those are basically the same problem. I don't know of an easy way to show that. So that's why I say, who knew? So that really took that took a lot. And the other thing they did is, when we write the integral of x squared is equal x cubed over 3, that's easy. And I've made that point before in the past to some people by saying, my 2-year-old daughter actually, I knew how to do that, but she didn't know calculus. She just knew how to manipulate the symbols. My 2-year-old daughter at the time could not have solved a tangent problem, obviously. And that's an indication of just how easy these processes are. And they realized that. And what they did is, if you look at the techniques, there was a whole hodgepodge of different methods, some geometrical like Fermat, all the area problems were geometrical. And when I mean geometry, I mean like Euclidean kind of geometry. It's hard for us to understand. The second part of their genius was to realize that the tools that Descartes developed could be applied to the problems of finding areas and finding tangents. And that makes it just so much simpler. And not everybody agreed that that was the right way to do it. Like one of Newton's teachers, a man named Isaac Barrow, thought that that was kind of perverse, that you should use geometric methods because they're purer. And you saw some of that from that article that I wrote a long time ago that we looked at when we were looking at non-European mathematics. When I was writing about dirty mathematics, there was sort of like I don't know what you want to call it, but a sense that not every mathematics was pure, and some of it was kind of ugly, and maybe something that's perverse or to be defiled. So anyway, I think those two things are really important. And again, Cartesian analysis, it's hard for us to understand how important that was because we use it all the time. But it was ideas that Descartes developed that just slowly kind of spread. And Newton talks about that. He uses the phrase Cartesian analysis. Newton's focus was on power series as a primary object. Leibniz, on the other hand, even though he knew about power series, he also was very much interested in the rules for manipulating. And if you imagine calculus where the primary object is a power series, then there's no need for a chain rule. There's no need for there's no need for a product rule or quotient rule, because you're just doing integration and differentiation on series, which is really easy. You don't need any rules for it. You just up the exponent by 1 and divide by the new exponent, to take a integral, and to take a derivative, you subtract 1 from the exponent, put the old exponent out in front. So it makes life easy. And so that was his focus. And I'll talk a little bit about that. And then again, Leibniz was more interested, I think, in the mechanics and the processes and this notion of summing of really small infinitesimal things. So again, I'm not going to go much deeper into that. But not only did they formulate math differently, they thought about it differently. And that's kind of hard for us because calculus is calculus to us, you know. And then Newton had a really key idea, and he talks about this. And it was, I would have liked to have spent some more time on this, but there was a Flemish mathematician, Stephen, and in 1585, he wrote this innovation, a new calculating machine called the decimal system. And of course, we've hit upon this before, that the decimal system was used in India and it was used in the Arab lands, but somehow those ideas didn't get to Europe. So when Stevens came up with this, maybe he got it from them, I don't really know. It was this groundbreaking way to do calculations, and he was very interested in the commercial applications of it. So it's hard for us to realize, but the value of the decimals is as a calculating system, and decimals are easier to manipulate than fractions. You know, so you can get some sense into that. So Newton said, well, if a number is an infinite summation of powers of 10, well, maybe that's maybe some relation, what we would call a function, is just a summation of powers of x. And that was one of his key insights. And so he could take things like square roots and fractions like 1 over 1 minus x and some other things more complicated and turn them into fractions. And that was groundbreaking. I mean, turn them into power series. And then so to integrate 1 over 1 minus x, you don't do that. You integrate the power series. So you don't need like a use substitution or something like that. You just integrate the power series. And so one of the things I'd hope to look at today, and it's on the handout, but we're not going to get to it, was about how he manipulated series, sometimes to solve a differential equation. Again, and again, people were using summations. You know, I think we've seen some examples of that, but what was innovative was to put Cartesian analysis on them and then to be able to do calculus with them. That was what the innovation was. So all these ideas that were floating around in the 1600s, Newton and Leibniz kind of said, oh, they're really aspects of calculus, the system we're going to call calculus, and we have these nice rules for manipulating them. So it made mathematics easier, but it also opened the door to much, much more complex mathematics. Okay. And then the last thing I'm going to say, and I'm not really going to talk about it very much, I have a brief handout that you can read about it, and plus I have that article, but Newton and Leibniz in the last part of the 17th century and the early part of the 18th, they were involved in this dispute over who discovered calculus first. I think they realized that they had done it differently, but for some reason, it was very important to know, for bragging rights or for other stupid things, other alpha kind of behavior. It was really important for them to like say, I did it first. And it sounds like both of them were egged on by others. You know, like you can imagine somebody, a lesser mathematician, saying, Newton, look what Leibniz, he's saying he did all this, but you did it first. And then Leibniz didn't evidently want to get involved, but then his buddies were saying, you can't take this, you know, someone, you know, so they got into like an intellectual brawl, and nobody comes out good here. The British got sort of stuck in a mathematical system using Newton's notation, which we barely use today. And the Continentals used Leibniz, and for some people say that's why 17th century British mathematics, 18th century British mathematics was kind of stagnant while things exploded all over the continent. So that may or may not be true. But anyway, I'm going to let you read more about that. So I just wanted to that's all I'm going to really talk about in terms of lecture today, but I wanted to just sort of try to tie together some of those ideas. And I don't know if there's any questions or comments on that.
Is it true that Leibniz killed himself because of this conflict with Newton, I guess?
No, I've never heard that. He died. I don't know much about him. And there's there's 3 novels called, what's it called? The Age of Reason by Neil Stephenson. It's kind of like science fiction, but it's about Leibniz as a central character in some of those. And he's quite the character in there. And I know that he died without many means. And so maybe that's how the story got. I'm not sure. I don't know enough about his life to know whether the priority dispute affected his livelihood or whether it was just his personality. He did a lot of different things. And like a lot of people that don't follow a single path, if it doesn't lead to riches, and it can lead to ruin or riches, if you're an original. So I never heard that he killed himself or anything.
Okay, thanks. I wasn't
Yep.
sure. I think I heard it somewhere, but I
Yeah.
wasn't
Yeah.
sure.
And the other thing is, I wanted to say something else too, and this is that reminded me. I should have put it on here as a 9th point, but that Newton apparently got into the calculus. There was a plague, and so he left. He went to school at Cambridge, and so he went back home. He was from the country, a town called Woolsthorpe, and so he went back home, where the apple evidently fell on his head, and he didn't have, like us, except he didn't have an internet. So like he invented calculus because he was in a pandemic. Let's put it that way. Didn't have much to do with his time, and so he read Descartes and some other things evidently, and I don't know enough about it, but people who I trust say that he was interested in these ideas for their mathematical content, and not for like solving problems of physics. Though when I present things today, you're going to see that there's a physics aspect to them, a dynamic aspect to them. So it would make sense that he probably wasn't unaware that they had other applications. That's not what I'm saying. But he created calculus during the pandemic. Okay. Okay. So download, rather than break into groups, I think the problems need direction. And I think if I put you in groups, you'll flounder. So I think I'm just going to go over the problems and let you work on them together, like we did a little bit last week. And I will go from the ground, rather than go from the sky to the ground like I like to do. I'm going to go from the ground to the sky. So I'll be more practical about how to solve the problems than I was on Tuesday. Like I say, I get carried away with that Leibniz triangle that, I got a little bit carried away about that. So I don't think it was to the groups that people understood really what was going on. Okay. So look at 19, and I there's some things I would be writing on the board, but I figured I'd write them here just because they are important. And I'm going to share the screen just so I can make notes. And so I'm going to get handout 19. And hopefully you're seeing that. Okay. I don't know whether Zoom has approved or my ability to use it, but it seems like that, like what I'm trying to do seems to be happening a lot more than it did when I first learned Zoom. And I always thought it was kind of random with screen sharing, but I think it's me. I saw Dan's, you're not doing absolutely nothing. Okay. Sorry, I just want to get rid of a couple things on my screen. Okay, good. Okay, so there we are. Okay, so when we think about an x, he called those things fluents. And really what he did is imagine here's a curve that's flowing. And notice I kind of drew it in that direction. And I kind of imagine that if this is parameterized by time, that time is flowing forward. As t increases, so does the curve. It keeps flowing wherever it's going. It could go back on itself, but it's where its position is dependent upon time. And if we look at a plane curve can be written like this. And if you scroll down a little bit, you'll see an example, which I just highlighted. That's a plane curve that mixes up x's and y's. And then another way to think of a plane curve is like a level surface of a three-dimensional function. So if you're used to thinking about a function like this, z equals f of x, y, like in Calc 3 or 110 in the spring, which I'm glad we can offer again. This would be the level curve z equals 0. Okay, so you can think of it that way too. That's not the way Newton thought of it, but any plane curve is going to be of this form. Though Newton did not use functions, this is his notation right down here, that curve that I circled. That's exactly how we wrote it. Except he tended to write, I don't know if he did it there, but oftentimes he wrote x squared like that. even though he used exponents for cubes and other things. I don't know why. But, okay, so we have this notion that on this curve there's points x and y, and they flow with time. That's supposed to be a comma. So really what they are is parametric equations where their position depends upon the time. Okay, so a very dynamic idea and one that's close to physics. We just think of them as points on a curve, at least I do. Okay, so then this, and this is used in differential equations still, that's going to be the velocity of x at time t. So you can think of x dot as equaling x prime of t and y dot as y prime of t. And along that line, if you have y dot over x dot, how would you interpret that? And don't think too hard, don't overthink it.
Is that going to be the derivative of y with respect to x?
Yep, dy dx. So if Leibniz was writing it, he'd be using dy here by itself as an object in its own right. And then if he were writing this, he would write it this way. Okay. And Newton didn't think of the derivative. Rather, he thought of the rate of change as a relation between x prime and y prime, just like this is a relation between x and y. But occasionally you see examples where he did do this. Because once he did that, then he could integrate it. Because then everything would just be a power of x. So anyway, now this is weird. It's a letter O, and that's going to be a really small time interval. And so here we have time, infinitely small time times an infinitely small velocity. What do you get when you multiply time times velocity?
Is it displacement?
Yeah, it's just going to be distance. So what this represents is just going to be a change in distance, a really small distance. D's bad notation has nothing to do with this D, I don't think. No, I don't think it does. What would this represent in modern terms then? How would you write that if you had to translate it? I'll give you this. Think about this as a displacement, but what's it displacing? I mean, what's it a displacement of? What variable? X, right? And what do you call a tiny displacement of X? Delta X. So we can translate that to this as a way to make sense of it. Okay. I'm just going to check the chat, which I haven't done in a minute, to see if there's any questions. Sorry, I have to get my cursor back, but are there any questions as I do that? Okay. Okay. So again, you can read this. This is just what Newton said about what he was doing. You know, it's his description. But reason I gave it is because he uses that term infinitely little. You know, and he uses terms like that. Okay. And this O dot X or O dot Y is what he calls moments. Yeah, so he has his own vocabulary. But since he's inventing this stuff, he has that right. Okay, so any questions about any of that? Okay. So as a I'll get rid of all that stuff. So as a problem, what he wanted to do is he wanted to take this curve and find the rate of change. And that would be to find the relation between x dot and y dot. And he had two different ways to do this. And this is going to relate to implicit differentiation, which I'll go over in a minute. We don't need to know that yet. So basically what he does is he takes that x and he tweaks it just a little bit. So I'm doing it for all the x terms. So you would do that here and here. And then you would do that with the y terms. And plug these in, and then you do a bunch of calculations. I want you to do all those. And I want you to, even though Newton didn't do this, is to solve for y prime. First is to solve for y prime, y dot, x dot. But to do that, what you're going to do is you're going to expand all this. And then, I'm sorry, expand this. And remember this quantity is equal to 0. So if you can group terms where that happens, you can get rid of that. And then you're going to divide by any common terms, and things should be simplified. And so that's what I'm asking you to do here. And I'll kind of like, it's just so long, it just takes a while to write here. So let me write that on the camera for a second. So I'm going to stop the share and come back to it. Just to give you a start, so you're not going to be floundering. Okay. Oops. Okay, so I'm going to start with this. Oh, and by the way, I have the links to where Newton actually did these things, so you can look at them if you want to see how he did it. And we're just using his method. And he had two methods. This is the first one, and then I'll give you the second one. So again, I'm going to replace this by x plus O dot x and cube it. And I'm going to replace this x by the same. And these are a's, they're meant to be general. And I don't know why this particular problem was important to him. And then do the same thing with y cubed. Sorry, let me pin this just so I can see it better. And everything's equal to 0. So again, you just want to expand everything out. So you'll get x cubed plus 3o x dot x squared. And just to help you get going, the next term is 3 first term to the first power, second term squared. And he wrote it OO x dot x dot. You can write it squares if you want. And then the last term is going to be OO x dot x dot x dot. And then you're going to do the same thing for all these other. This is a square. I forgot to do it. So again, I'll do this, but I'll let you do it on your own, and then I'll just do it kind of behind you so you can check. Does that make sense though? What I'm asking you to do? Okay. And then if you remember implicit differentiation, if you get done before we're done talking about it, you can check your work with implicit differentiation. But I'm going to go over that. Oops. I didn't mean to write O dot if you're watching what I'm doing. So I don't know where you are in your calculations, but in my calculations, I found the x cubed, the minus ax squared, the axy term, and the minus y cubed term. And I know that together, those equal 0 because of my initial condition there. So I could get rid of those. And notice that every term has a y in it. I mean, has an o in it. So I'm going to be able to divide out by those o's. So can anybody figure out a shortcut to get rid of terms? Like I've divided out by O. I know I really would like to work the other way around, but I don't have enough space. But can you figure out a shortcut where you can get rid of unnecessary terms? Remember, we've divided out by O, and we have a lot of little o's left. And remember, O is a really small piece of time. What do you think is going to happen to that O? What are we going to do to it? Like what happens to delta x when you're doing a derivative? Or your h term? O goes to 0. Okay. So that's going to be what he's going to do, and that's going to get rid of all those terms that have an O in them, and those happen to be terms that have a higher order differential. So that was the shortcut, is you can get rid of all terms with a higher order differential, because after we divide out by the common term O, all the terms that have like a second or third order term are going to still have an O in them. So we can, and what's going to happen is just like with h going to 0, when you do a derivative calculation the long way, all that's going to go to 0. And so what I'm left with, these should be arrows, not equals. Okay. I end up with something like that. Hopefully you do too. So again, I expanded everything out. I got rid of all 4 of these terms because together they equal 0. Then every term has an O, so I canceled out an O from every term. And then just like when we do a derivative calculation the long way, you let O go to 0. And so that gets rid of all those higher order terms. And then when all's said and done, you have that. And if you look to see what Newton did, if you click there, you'll see that's what he did. And so I'm going to recopy this neatly. Okay. And that's what I'm left with. And it's conceivable, let me put it this way, it's not inconceivable that I made a small calculation error. So if you have something a little bit different, it's probably, I'm not going to worry about that. Okay. And then what I want to do, I want to solve just for our sake, not for, Newton was happy with this. This is a differential equation involving the motion of particles described by that curve. You can look at it that way. And like I say, when you look at differential equations, especially if you look at a British book, you'll still see these dots. I remember seeing some of those in graduate school. Okay. So what I'm going to do is I'm going to get all the y dot terms on one side. Because I want to solve for x dot over y dot. You'll see what's going to happen, I think, after I do it. And then I'll keep all the x dot terms over here. And then notice that I have an x dot term here in every term, so I can factor that out. And I have a y dot here. Then I can divide each side by x dot and each side by 3y squared minus x. Those cancel, that cancels, and this is what I end up with. And what that would represent to us would be that curve that I drew, which doesn't represent this necessarily. This would be a tangent to that curve at a particular point, x and y. Okay. Okay, so questions about that? Okay. Yeah, so Paul has a lot of weight on his shoulders because I looked at him, and if he says yes, then I go more, and if he says no, then I think I'm okay. So he's speaking for all of you. Okay. Okay. So hopefully that makes sense. I mean, and again, I gave you two choices for questions for Newton on the exam, and this is one of them, and the other is what we're not going to get into. So I'm guessing you'll do this one. Okay. See what time it is. Okay. I'm going to skip the implicit differentiation. I'm just kind of curious. Has everybody had implicit differentiation? And if not, just let me know. Because I know I got into trouble assuming too much knowledge before, so I don't want to make that mistake again. So if you haven't had implicit, okay, unsure. Okay. It could be one of those things that teachers expect you to remember, but that, we expect you to remember everything. But you might have learned it. It's way back in the mist of time somewhere, buried among all the other stuff. Yeah, somebody says it was 4 years ago. Yeah, got it. Okay, I'm not going to go over that now just because of time. But this is the technique. If you've had it and it's fresh in your mind, and there's no reason it should be, what he's doing is essentially equivalent, not the same thing, but you get the same result as if you do implicit differentiation. Okay, and that's method number one. And so we're going to take that same curve and do method number two. And I think I'm going to share the screen. So you can see both of what he did here. But before I do, is everybody good with that calculation? Again, pretty much the one thing I didn't say on the sheet is, I did say get rid of get rid of high order terms with an O in it. Yeah, so you let go to 0. I didn't say it quite the right way. Okay. So I'm going to look at these. I'm going to share for a second and look at these. But let me get to the place we want to be first. Okay. So I just want to have it all lined up so it is there, but now I have to find it. Yep. Okay, good. Okay, and this might have been written in English. I know some of he wrote in Latin, and some of the stuff he wrote wasn't meant for publication, and some was. He was very, very, very hesitant to publish anything. I don't. He was a weird guy, but that's part of it. You can read all kinds of weird stuff about him. But, okay, so I'm assuming you're seeing the page. It says the and so if you look right here.
We're actually seeing your email.
That's not good. Okay, thank you for letting me know. I hope it was interesting. Okay, let's try this again, the method of fluxions. How about now? Good, okay.
Good.
Thank you. Thank you for letting me know, Molly. Okay. I've managed not, as far as I know, to embarrass myself on Zoom. And I want to keep my streak intact. Okay. So you can see that he's starting here, and then he's like doing a lot of calculations with it, and he's going through what he did. And that's just kind of what we did. And he ends up, he explains why he does what he does, and he gets down to here. And you can see his notation. I don't know why he writes x times x squared here, but oh, that's x dot. I'm sorry, my bad. Okay, so you can look at it there. And then the next method we're going to do is 4 pages earlier. And let me clear off this junk. Good. And it's right here. I don't know if you can see what he's doing. It's the same curve, and he's just giving us a different method, but he's multiplying the term by 3x dot divided by x. Here he's multiplying the x squared term times 2, and then here he's multiplying only the x term by x dot times x. And then he's doing everything to the same thing to the y term. So what's he doing? Like is it kind of, do you see what that accomplishes algebraically? What does it do to the power of x? It decreases it by 1. And then it adds that x dot term. So he's basically taking a derivative. So this is his second method. And the first method sort of is more conceptual, because it's like it's like taking a derivative the long way, like you first learned. And this method is more like algorithmic. Let's get it done. Okay. So let's go through that with the same problem. So I'm going to stop the share. And then, so that would be problem number 4 on the sheet. And again, I'll let you read. Remember, multiply all the terms times, I explain there what to do. So, and then if the term has both in it, you do all the x terms first, and you do the y terms too. Okay. So hopefully you end up with something that looks like that. And that's what we had before, I hope. I'm just going to double check. Oh, I think I dropped a couple of A terms. Yeah, I dropped a bunch of A terms, but otherwise, yeah, that's right. So that was just a mistake when I dropped the A terms in the other one. It's just being lazy. Okay. Okay. So which method do you like better? You know, obviously the algorithmic one, but again, think about what we do. I mean, nobody wants to take a derivative by hand all the time. You use the formula. So he was giving a procedure. And as I mentioned, this procedure, there were people that were doing calculus-like things on one side of the equation, like maybe on the tangent side. Probably not on the, as I understand it, on the area side. Again, it was putting them all together was one of the big things that they did. So they were using other people's ideas, but just creating this new kind of novel synthesis and profound synthesis. Okay. Okay. So, and again, we can solve for x dot. We could solve for y dot x dot. You would get all the x terms, x dot terms on one side. Factor out the y dot. Factor out the x dot. And then solve for y dot over x dot. And this is the correct one. So that should be a minus sign here. I shouldn't have started bragging that it was correct. Okay. Okay. So again, yeah, so a couple of questions here. Why do you think he gave, what do you think he was trying to say by the fact that both methods work? Any thoughts on that? Was he trying to make a point? And think about rigor.
Maybe try to verify results.
Yeah, I mean, to show that that the method that he do from first principles, which was the one that, you know, where you even that had problems. That was problematic though to some people, but you know, because it's kind of like mystical. First you have the O and then you don't, you know, then you let it go to zero. And that was criticized after his time by a man named Bishop Berkeley. But this was maybe a way of showing that, yeah, that if I do it by first principles, that amounts to doing this algorithmic procedure. You know, I don't know for sure. And then if you look at this term, notice we have it here. And we do that same procedure again to the same term, but with respect to y. What rule is that implicitly? It's a product rule, right? You know, he's saying that the derivative of axy equals ax derivative of y plus ay derivative of x. But in our world, that's x dot. In our world, that's going to be equal to 1 because we live in a world in an x world, where x is the independent variable, and we're differentiating with respect to x. In his world, it's kind of like in the Calc 3 world, where the derivative of x, like x dot x prime of t, is not 1. So again, it's a different way of looking at things. He's not thinking of x and y the way that we do. My sense of Leibniz, but he was closer to what we were doing. And again, it took time for people using calculus to sort of sort things out together. Okay. So there's something I wanted to do last class that I'm going to do this class. I mean, I'm always tempted. Oh, I have 15 minutes. I can do. We could do more here. I could do the stuff on the backside, but I'm not going to try to do that today. But I kind of want to give you a visual proof of the product rule. And so we're looking at the rate of change here. And so I'm going to visualize these as a box. Can you see what I'm doing? Let me write a bigger box. I think I boxed myself in. Ha ha ha. Okay, so I'm taking, this is my x plus delta x over here. And this is y plus delta y over here. And so when I go through this, I'm going to get this area as xy. This area here is y delta x. This area here is delta x delta y. And this is x times delta y. So our derivative is the rate of change, this minus this. And so when you do that here, you're going to let both of these terms go to 0. And what you end up with is xy plus y delta x plus x delta y. Actually, I'm not going to let it go to 0 yet, plus this. And what you're left with are these terms. And so that's a suggestion of how some people may have like sort of figured out the product rule. Oh, you still have this term right here. As you can sort of visualize the product rules that change. And since both of these changes are very small, these are like doubly small, and so people ignore them. So I don't know. So that's one way that's one way. And so if you look at that was motivated by this question here, like why we had two terms here, one for each variable. And that was just one, this is one way that maybe it shows up geometrically that he might have thought about it, why you had those two terms. Anyway, okay. And there's also a visual for the integration by parts that's a similar, I'm not going to do, which derives that, but I'm not going to do that. But anyway, I think that's a good place to stop. And I don't know if there's any questions about anything I did today. I'm going to say a couple of closing remarks and then that, briefly, and then that'll be it. But questions about today? And are there questions about the course or about like, oh, thanks, yeah. Or about sort of what happened next in the history of math, or what happened further? Like I know Daniel had that question earlier about Leibniz, but do you have any questions about sort of what were the next steps, something else that you've studied that you're curious about?
Yeah, just so I could put this kind of in perspective, when was like real analysis kind of started to be studied, I guess?
Okay.
Or...
So almost immediately after what Newton did, you know how we let that little O term go to 0? Bishop Berkeley was like, you can't have it both ways. You know, how can it be something and nothing? And he called those things when they disappeared ghosts of the things that remained. Because, you know, some of the things disappear, but not, you know, like the first, like here, the delta x and delta y's stay, but the delta double term goes away. And so Bishop Berkeley would say, well, how can you do that? And he called the things that remained, like the differentials, like ghosts of departed quantities. And he asked people like, you have to prove that that's actually valid. You haven't really you've given me an intuit. You've given me something that seems absurd and intuitional, but let's find real proof of it. Okay, that was one of the ideas. People argued over what a limit was, and how to define it. And I remember reading something a long time ago that, if you look at the curve y equals sine x over x, it goes like this. It oscillates, but the oscillations get to be tinier and tinier, so we say the limit is 0. Some people would say, well, why is the limit, that it's not, people say the limit's when you approach one quantity but never reach it. And somebody would say, well, this reaches 0 infinitely often. How can 0 be the limit? And that's because these things weren't defined very well. And so there was a lot of discussion about this. In about 1820s, Cauchy, whose name you might have seen in courses, he started to sort of he sort of defined, not completely, limits, let's say. And then the limits are at the key of calculus. The limits are at the key of the derivative. They're at the key of the integration. And so then but still there were holes. In about 1869, I think is when the paper came out, Weierstrass. I don't know if people have heard of him, but he used the definition we use today. And if you've had that course, that would be the epsilon delta definition. So real analysis came out of those kinds of questions. And then sort of a question that happened in the late 1800s was, you could have functions that are, let's say, Jordan integrable, that aren't Riemann integrable. And Riemann sums comes from. So there was this sort of controversy about what does it mean to integrate? And people didn't understand integration very well. And so that was another motivator of some of the more advanced analysis. Questions like that, like what do we really mean by an integral? Why can we use one system of integration and integrate some things but not others? And something called measure theory came out of that discussion. So it was answering those kinds of questions. And then once people had proofs, they kind of got carried away and overreacted and wanted to prove everything. And so that question we had earlier about non-Euclidean geometry, really what was going on there, that also, I think, was part of that ferment of analysis. Like, we really have to figure out really what the truth is behind the parallel postulate. I think was another big motivator. When does it work, and that kind of stuff. Okay. So other questions? Okay. So I guess that's it. I think you all deserve a pat on the back. I assume this is the last class for most of you this semester. And I appreciate your patience for meeting after the break. I was really hoping not to do that. And, I hope you feel the same, but I'm not fishing for compliments or the opposite, but I really like the way that the presentations worked out. And I was really pleased with the work you did. And I've taught this class, and I don't think I've ever had a class that is on board as you all, and especially under these really difficult conditions. And so I really appreciate that. So that's good. And good luck with your finals. Good luck with what you're doing. And I posted office hours for next week, and I can find other office hours, and we can always meet during these time periods to do for the finishing off the problem set. And I have next Thursday is the deadline, but I'm going to be really fluid about that. Grades are due 2 weeks from yesterday at 10 a.m. I'm sorry. So I need to have things in no later than like late Monday night to really grade everything. So, and by Monday, I mean Monday after the week. So do your best to try to get things done early, but be in touch if that's not working out. You're allowed to work with other people, but I want you to write up the papers separately. And if you've had me before, you've heard this, but like work with up to 2 other people, let me know who they are. And I don't like to see 2 problems that have the same wording, 2 answers. So like the best thing to do is to work with somebody else and then go off on your own and write it up. So it's going to be in your own words. Okay. Okay. So good luck. It's been fun. I can't wait to see you all again in real time rather than on Zoom. So my hope is by capstones that will happen. Okay, so have a good evening.
Thank you, Professor.
Daniel, I have a
night.
question for you, Vizcara. Do you have a brother?
Yes.
Is it Drake?
Yes. Did you see him in some class?
Mateo? Yeah.
Yes,
Yeah,
I
yeah.
do.
He looked like you. I said, I wonder if that's his brother. Yeah. So anyway.
Yeah, but this last name and looks like me. Yeah.
Yeah. Yeah.
He's my brother.
Yeah, I was
Where did you see him?
CS65. I was observing Professor Klingy's class. So, and he was giving a presentation today.
Oh,
He did a good job.
huh. Yeah. Well, he's also a math major, so I think you might see him at some point in a class.
Good. Yeah.
Yep. But yeah, anyways, thanks a lot for the class, Professor. I really enjoyed it.
Well, me too. Thank you.
Was a good class. Have a good break.
Yeah, you too, Bryce. Yeah.
Have a good break, Dr. Alexander.
You too, Daniel. Get back to climbing when you can.